Hi, my name is Juan Perdomo, and today I'll be presenting my recent work together with John Miller and Tijana Zrnic on a paper titled Outside the Echo Chamber, Optimizing the Performative Risk. So our work is motivated by the following observation that oftentimes when we use machine learning within societal systems, um, these machine learning systems exhibit strong feedback loops, particularly when used in the context of decision making. An example of such a phenomenon is the problem of credit scoring. So we can imagine a setting in which an institution, such as a bank, is making loans out to individuals. The way by which this process might go about is that the bank collects historical data from individuals, such as their income, their credit history, whether they've defaulted on loans in the past, which ones they've been able to pay back. And based off this historical data, forms a predictive model which attempts to um, recover what is the future probability of default were the bank to give a loan to this individual. Based off this probability of default, the bank sets an interest rate, and this interest rate then influences the final outcome on whether the individual will be able to pay back their loan or not. The thing I'd like to emphasize about this prediction example and why we think that there's a feedback loop is that the predicted probability of default affects the true probability of default. For example, if the bank predicts that an individual will be high risk and has a high probability of default, then they'll set a high interest rate. This interest rate will make paying back the loan much harder for the individual and hence makes the true probability of default much higher. And then, of course, the opposite action occurs if we set a very low predicted probability of default. Notice that this recorded event then feeds back into the bank's data set and influences the predictions of the new classifier that is trained based off this historical data. In order to analyze situations like these, we've developed together with some collaborators this performative prediction framework. As a model, performative predictions tries to study these scenarios where predictive models impact decision making and lead to model-induced distribution shift, i.e., performative effects. In general, these predictive models and feedback loops have the following form, where data is used to train a predictive model that then influences decision making, such as whether to give an individual a loan or not and what interest rate to give them. These decisions then affect the state of the world, which then generates the data that feeds back into the creation of our predictive models. The key feature of performative prediction is that each model is associated with a potentially unique distribution over instances. A particular default model induces a distribution over defaults over a particular population. Relative to supervised learning, this arrow that feeds from decisions to the world is ruled out in classical frameworks. A key assumption within supervised learning is that our predictions cannot affect the underlying distributions. These frameworks assume that there is a single fixed distribution from which the learner is observing instances, and the predictions the learner makes do not affect the data generating process. Great. So with that in mind, we can start to see that performative predictions are everywhere. Once we realize that these feedback loops exist, we start to notice them in a number of different settings. For example, election forecasting. If we predict that a particular candidate is likely to win an election, say by a landslide margin, then that might induce supporters of that candidate to stay at home. They might be as incentivized to go vote, seeing as how the candidate is going to win anyway. However, these predictions are performative in the sense that they might drive down voter turnout and change the electoral outcome. Similarly, whenever we predict climate models of the future or create climate models, these climate models are used to inform decision making by policymakers today. And these decisions that we make today in terms of policy change greenhouse emissions, the development of new technologies, which then affect climate patterns in the future, which is the very thing we're trying to predict. We don't need to go to such grand scale examples. These performative predictions are something we exhibit every day, say when we're commuting to work. When we're trying to go from home to work, or say to the DMV, we might load something like Apple Maps or Google Maps and look at the predicted time of arrival along a particular route. If the map app determines that a particular route has a low ETA, that might drive more users of the platform to drive along that route, thereby increasing traffic and increasing the ETA. So in this setting, we can think about this like a self-negating prediction. But I'd like to emphasize that in all these examples, we think about them as being performative, since our predictions affect the true distribution over the observed data. Great. So with this motivation in mind, I'd like to talk now about what our results are and what our contributions are in this paper. And at a high level, what we try to do in our work is we try to tackle the problem of finding classifiers that are capable of making accurate predictions, even in these performative settings where the predictions the classifier induces can change the underlying distribution they observe. Due to these feedback effects and distribution shifts, this optimization problem can quickly become non-convex, even if the performative effects are relatively simple and the loss by which we measure accuracy is convex, say like something like the squared loss. Our main results are that we identify a set of conditions under which the performative risk is convex, and then having established conditions under which this optimization problem is tractable, we compare different algorithms for solving them and for efficiently computing optimal classifiers based off data. Great. So to formally set up this problem and set up our contributions, I think it helps to establish some common knowledge and definitions regarding exactly what performative prediction is. And perhaps the best way to do this is by contrast to classical prediction or supervised learning. So in supervised learning, we assume that data, we use Z to represent data instances, which we should think about as pairs of features X and outcomes Y, is distributed according to a fixed distribution D. In this setting, the goal is to minimize the expected risk of a classifier parameterized by a vector theta. So where the risk here is the expected loss of the classifier theta, or predictive model theta, when data Z is drawn from a fixed distribution D. In performative prediction, there is no longer a fixed data distribution. Each model's theta, or again, theta ascribed to the parameters of the model, induces possibly distinct distributions over observations d theta. Here, d theta is what we call the distribution map. And this mathematical object of the distribution map is the key conceptual innovation of the performative prediction framework and what sets it apart from more traditional models such as supervised learning. So the distribution map is used to describe the distribution induced by a classifier, such as, for example, in the context of traffic prediction, the distribution over travel times induced by a particular ETA model. Given that each classifier or model induces different distributions, the goal in performative prediction is to minimize not the risk over a fixed distribution, but to minimize the risk observed by a classifier when it is deployed. And we call this the performative risk. So relative to the, say, classical supervised learning risk, the performative risk is the expected risk of the classifier theta over instances Z drawn from the induced distribution d theta. Great. So a common approach in practice to deal with distribution shift is to retrain. Whenever we have performative prediction in practice, these things are often interpreted as just a passive distribution shift, in which case a common solution is to repeatedly retrain. A schematic by which this might work is that a practitioner deploys a machine learning classifier. This machine learning model leads to new actions which change the observed distribution. Having observed that the classifier model is no longer acting as it on the previous data that was collected, since there is now a new distribution shift, the system designer then retrains the new model on the new distribution shift and redeploys. More formally, we can think about retraining as the following procedure, whereby given a classifier theta t, we collect data from that distribution and find the risk minimizer on that distribution d theta t. This leads to new classifier theta t plus 1, which we then redeploy, and the process repeats. These ideas regarding retraining were the focus of most of the previous work on performative prediction, and we say that a classifier or predictive model is performatively stable if it is a fixed point of retraining. That is, stable classifiers have the property that they are optimal for the distribution that they induce, in the sense that if we deploy a performatively stable classifier and then retrain, we'll get back the same solution. However, while stable classifiers eliminate the need for retraining, these models can have poor predictive performance. In fact, one of the main contributions of our work is that we showed that stable points do not necessarily minimize the performative risk in any reasonable sense. In fact, they can maximize the performative risk. This gap between stable points and optimal points, whereby optimal points, I mean models at which minimize the performative risk, holds even if the performative effects are small and the loss is well conditioned, and even in cases where the performative risk is strongly convex, which is quite a strong assumption. In order to understand this phenomenon, a useful analogy to have in mind is that we can think about performatively stable classifiers as an echo chamber in an online platform. And members of an echo chamber might be reassured about their ideas by voicing them within this small community where everyone thinks alike. However, it's not clear whether these ideas are valid more generally. Similarly, in performative prediction, the predictions of a stable classifier look optimal on the distribution that classifier induces, but it's often the case that there are other distributions that could be induced by different classifiers, which lead to an overall smaller performative risk. I'd like to note that most or all previous work on performative prediction has focused on finding stable points, and there are no known algorithms. Before our paper, there were no known algorithms for finding performatively optimal classifiers. Great. Seeing as how performatively stable classifiers can in fact have very poor predictive performance, we need to develop new algorithmic ideas that go beyond passive lead retraining, since passive lead retraining can at best lead to stability. These ideas need to actively anticipate performative effects and hopefully converge to solutions that have much better performance. In order to successfully carry out this optimization procedure and find performatively optimal classifiers, the first question we consider is, when is this optimization problem actually tractable? To state our main theorem, we first introduce two of the key definitions which go into our result. The first is this notion of Epsilon sensitivity, which captures this intuitive notion that similar predictions induce similar distributions. Formally, it states that the distance between two different distributions, d theta and d theta prime, that is, the distribution induced by theta and theta prime, are bounded by a small constant epsilon times the L2 distance between theta and theta prime. The second is this location scale assumption, which in fact places a structural assumption on the form of the distribution map. It states that that instances drawn from d theta are equal to some base distribution z0 plus a linear shift in theta. In short, it states that these performative effects are linear in theta, where the linear shift is captured by this matrix mu. With that in mind, we can now state our first theorem, which states that if the loss is gamma strongly convex and beta smooth, and the distribution map d theta forms a location scale family and is epsilon sensitive with epsilon less than gamma over 2 beta, or half the inverse condition number, the performative risk is convex. Furthermore, this theorem is tight in the sense that if we delete any one of these assumptions, so if the loss is not strongly convex or not smooth, or epsilon is strictly larger than this threshold, then we can come up with a counterexample showing that the performative risk satisfies the remaining assumptions, yet is not convex. So having established the convexity of the performative risk, the next natural question to ask is how we might go about optimizing it. The key difficulty of optimizing the performative risk is that gradients of PR theta are generally unavailable. While we can always take gradients of the loss, theta in the expression for the performative risk appears in two places. One is the loss, and the other is the expectation. Remember, the expectation is taken with respect to the data distribution induced by theta. And in settings where the distribution map is generally unknown, then we can't differentiate with respect to the second argument. However, there are known algorithms for optimizing convex objectives when gradients are not available. There's a rich literature on derivative-free optimization methods, such as these gradient descent without a gradient style algorithms, such as the one presented in Flaxman et al. However, these algorithms generally suffer from high variance and a slower optimization rate. With that in mind, we introduce a two-stage procedure for optimizing the performative risk, which consists of the following steps. In the first one, we perform experiment design and deploy random classifiers in order to observe their induced distributions. Using the collected data, we can find an approximate model of d theta using least squares. This is in the context of the location scale family example, where d theta satisfies a particular parametric assumption. Using the collected data and the approximate model, we can then we can find the optimal solution on a proxy for the performative risk offline. We show that under appropriate regularity conditions, and assuming the performative risk is already convex from our previous structural analysis, this two-stage procedure converges to the performative optimum at a rate of d over n, where d is the problem dimension and n is the number of samples. This is the standard parametric rate we might expect. However, we can recover this rate even in settings where the gradients are not available to start with. In addition to these optimization results, we evaluate these ideas in a number of different settings, particular in strategic classification, as well as in a synthetic data regression example that exhibits performative effects. As established previously, we find that in these simulations, there are large gaps between stable classifiers and optimal models under the various different settings, in particular under strategic classification. And we find that the two-stage procedure significantly improves upon the performance of previous retraining style algorithms, which converge to performatively stable points, and derivative-free methods, which also converge to performative optimum, but a much slower rate. So with that, I conclude the discussion of the main results of the paper. However, before finishing the talk, I'd like to look forward and talk about some of the questions that I think are interesting directions for future work. Relative to more classical settings like supervised learning and formative prediction, the learner has agency over the observed distribution, and this introduces new concerns that aren't necessarily present otherwise. In particular, the system designer must balance between a desire for predictive accuracy with the social welfare of those who are being classified, and other externalities that arise from the induced data distributions that come from our predictive models. These objectives must be carefully evaluated within the relevant social context to inform the kinds of algorithms and exploration that the system designer carries out. For example, in a credit scoring example, as I mentioned earlier, there are a number of failure modes that could arise from performatively optimal classifiers. One of which that we could potentially imagine is that the choice of predictive classifier, if we assign everyone a very high interest rate, we'll assign a very high interest rate, thereby making it almost impossible for any loan applicant to be able to pay back the bank. In other settings, such as financial trading, it may be sufficient to mostly focus on predictive accuracy. A full treatment of the interactions between predictive accuracy and social welfare we believe is an important direction for future work by the FORC community, and we look forward to chatting with you all at a conference over the summer. Thanks.